please. Number 1742. I search presenters. Is Mikhail Kvasny, Vladislav Shevchuk, and Halina Klim. Is here? Okay, and one more presenter of our section. Marina Derkach, Danila Matyuk, and Inna Skarga-Bandorova. I saw that Danila Matyuk will.
Yeah, I'm sure.
Oh, Danil, sorry. Can you now present your?
Yeah, okay.
Okay, welcome.
Can you see the presentation?
Yes, we see, and welcome for your presentation. Please 12 minutes. Okay, thank you.
Okay. Today I'd like to present our result on developing autonomous quadrotor flight stabilization system. So you can see the topic here. First of all, we're going to discuss our motivations that raise it not only from our side to achieve an effective autonomous stabilization system, but also from our analysis of state of the art in area on small multi-robot drones. Then we talk about the objective of the research. We will also show a case study and main results from a real assembled quadrotor. And finally, we make some conclusion and feature on next steps toward developing experimental quadrotor configuration. So let's start. Recent years, small multi-rotor drones are great interest in science. They're light, maneuverable, and relatively cheap. However, due to their simplicity and low rotor latency, quadrotors are also more challenging to stabilize, especially in the gridded environment or when external controls such as GPS are denied or unavailable. For this reason, we denied that effective autonomous quadrotor flight stabilization system requires a good solution for the following two tasks. First, it's determine the position of the quadrotor in three planes, the angle of inclusion relative in the Earth's surface, and calculate the deviation from the required position. And two, it's apply control signals to compensate for the deviation and bring the quadrotor to the required position during the proportional integral derivative control, its speed control. So we start from primary analysis of state of the art and the topic of autonomous flight stabilization of small multi-rotor drones. Some paper with the most prominent result are presented in this slide. This work aims to develop an effective autonomous quadrotor flight stabilization system, science both the PID controller, the complementary filter, and easy to implement. The stabilization system based on them and less resource intensive, and this is an important nuance from working with low power quadrotors. The PID controller calculates deviation compression and brings the quadrotor to the required position. The complementary filter is used to improve the accelerated tilt angle calculation relative to the ground. Our next slide includes result of solving full subtask, the design of flight stabilization system based on the complementary filter algorithm and PID controller, experimental configuration of the quadrotor and testing result. Figure shows a block diagram of proposed flight stabilization system based on the PID controller and a complementary filter. The PVM level controls the rotation speed of the motors X, Y, and Z, the specific angle along the X, Y, and Z axis, respectively. A signal is applied to the microcontroller, which is converted into pulse-width modulation, its PVM signal. The correct angle is determined using a complementary filter, which calculates and sends an offset to the PID controller. The PID generates an output signal in form of a PVM signal to maintain the set position. The PWM implementation, the controllers consist of two blocks, is a linear integrator and three position relay elements. Science for flight stabilization, it is necessary data time of orientation of the quadrotor along the three axes. It's necessary to calculate the angles of inclusions using accelerometer and rate of change of the angle due to the gyroscope. By processing the angles of the three-axis gyroscope according, one can obtain the orientation of the object in space. By measuring the acceleration of the three axes of the accelerometer, linear accelerometer data can be obtained that is possible to determine the movement and fall of object or the push against an obstacle in order to bypass it. To calculate the deviation compression and bring the quadrotor to the required position when solving the problem of flight stabilization, a PID controller is used. When stabilizing, L3 axis must be taken into account normally, its roll, pitch, and yaw angles. Direct control is carried out by calculating an amount of effort with which the quadrotor tries to compensate the angles of deviation and each iteration of control period. The proper stabilization system was tested and validated on real assembled quadrotor. The components were used in the development of the quadrotor are presented on slide. For convenience, a double slide printer curved board was made using laser ironing technology in sodium persulfate, which is usually used to each printed circuit and copper. The board is based on STM32F4 family microcontroller and has a specific groove form shaped to be placed on specific frame model. Their sizes board correspond to the dimensions and quadrotor chassis, which also made it possible to place all the necessary components on it, thereby reducing the number of wires to a minimum and avoiding the additional servo board. The MPU 6050 has a programmable interput system that can generate an interput signal on an int pin, which generates a pulse every time the state of the pins change. In figure, pin A11 is responsible for clocking the I2C bus, pin A12 is for data transfer, and pin A15 is used for implementing an interput to fill the memory buffer in MPU 1615. For data exchange between STM32 microcontroller and GI521 model, we developed a method for connecting device via the I2C interface. Verification of the development method for reading data from the sensor register and performed as follows. Interput occur about 45 times per second. Each interput lasts about 22 milliseconds. 14 sensor indicators are processed and in one input, respectively at address. The gyroscope reading are discrete signs. They were integrated a microcontroller to determine an angle of deviation from the initial position. The method fully mimics operation of the sensor without loss of data accuracy and less costly quadrotor configuration. If such need areas, it is possible to increase the number of devices using free contact of the microcontroller without loading its memory, thereby simplifying calibration in case of orientation error and quadrotor flight stabilization. This slide shows the result of reading of the GI521 model when applying 10% of the power of the quadrotor engines. This is discussed about reading of the tilt angles for the test period are destroyed. As RMSE values are 36 degree and 16 degree for the gyroscope and accelerometer respectively. For clarity of the result, sensor data from the quaternion position, which used the gradient descent orientation estimation filter to describe the position of the body in space, is transformed. Table 1 shows that after the conversion, the obtained values are 39 degree for the gyroscope and 18° for the accelerometer. After processing by the filter, the value of RMSE equal to 3° was obtained, and through complementary filter, the error was 2°, which means the both filters give very accurate angle and unconditional of shaking and vibration. The result of the complementary filter shows the figure sensor reading from a quadrotor. The green line is the angle computed from the gyroscope reading. Gyroscope is subject to zero offset is stability, and which until 0 point on the gyroscope drift in time through the integration of the state of the position angle. That is, the error is integrated. As a result, the angle gradually increases. The red line is the angle according to the accelerometer. Over time, an external force acts on the sensor, which introduces an error in computing the angle of inclination. The blue line demonstrates the angle computed using the complementary filter, and therefore they condense of the red and blue curves. The point where blue curves begin to fluctuate means the state the pit controller, which tries to compensate for the deviation at quadrotor from the horizontal plane. When stabilizing, we need to take into account L3 axis, adding a pit controller for not only the roll edge, but also for the pinch and yaw angles. In figure, blue line indicates the quadrotor's deflection angles, and red one indicate the effort the quadrotor tries to return to the side position. Now a short video about how the first testing in the project took place. Okay. As a result of testing, the developed stabilization system confirms the possibility of its use in the construction of a quadrocopter. Two main tasks have been solved in the development of a flight stabilization system. Firstly, the position of the UAV and free planes is determined, the angles of inclusion relative to the Earth surface, and the deviation from the required position are calculated. Secondly, control signals are given to compensate for the deviation and bring the quadrocopter to the required position. Thank you for your attention.
Thank you, Daniil, for your presentation. Dear colleagues, any questions now? I see. Dr. Igor Kryushnikov, please.
Good day. Thank you for your presentation. My question is, do you consider in your devices case when one of engine of UAV failure? In this case, can this UAV fly over with this situation?
No, I haven't tested this situation.
Thank you.
Other questions? I have very short questions. Do you take into account in your experience, in your research, failure issues of components of UAV? I mean, influence of such failures on your system of stabilization.
Yes, of course, and on this basic, I regulate the coefficient for pit controller, and it's be many tests and choice the better coefficient.
I see. Hence, you take into account this issue by checking of changing your parameters. Yes.
Yeah, coefficient is more actually for setting stabilization. It's
yes, I understand that is a parameters which can change it caused by failure. Yes, and you check this coefficient or coefficients, and by such way you can check failures states as well. Similar one of the our previous presentation where this idea was demonstrated. It just not maybe question, just discussion issue. Okay, thank you very much, Daniil, and your colleagues for your presentation.